Welcome back everyone, and here we have another example involving an application of the derivative. Basically, we're going to interpret the meaning of the derivative in the given context. So here we don't have just a regular function y equals f of x, but instead we have a function that has a meaning, a real life meaning. So we have c equals f of a. C is the cost of building a house in dollars, and a is the area of the house that we are building. So the cost in dollars of building a house, a square feet in area, is given by C equals f of a. Now I can also write it like this: C of a, the cost as a function of area. Okay? Because the cost will certainly depend on the area, right? The bigger the house, more than likely the more the cost that are going to be associated with that. So first question is, what are the units of f prime of a? So the derivative of this function. So you can look at it as f of a or c of a. I think c of a is a little bit easier to think about. It's the cost function. So f prime of a is also corresponding to c prime of a. Okay, what are the units? The rate of change of cost per unit change in area. So you can also think of it this way: the rate of change of cost per unit change in area, dCdA. The units for the top variable divided by the units for the bottom variable will be our answer. So this was dollars, this was square foot. So the answer will be in terms of dollars per square foot. So f prime of a, equivalently c prime of a, represents the rate of change of cost per unit change in area, and the units will be dollars per square foot. So what is the meaning of f prime of a? As I just said it, and let me write it down this time. It represents the rate of change of cost in building per unit change in area. So what this really tells us is, roughly speaking, this is cost per square foot. So per unit change in area, that could be like when the area changes by 1 square feet, how would the cost change? So this will roughly tell us cost per square foot. So now we're supposed to interpret the meaning of f prime of 2000 equals 100. Again, you can think of it as c prime of 2000 equals 100. So remember, the number inside is the area. The number outside is the cost in dollars. Okay, so the rate of change of the cost function at the moment when the house is 2000 square foot is roughly $100 per square foot. So what this tells us is the cost is increasing at a rate of $100 per square foot when the area is 2000 square feet. That is the cost of getting to 2001 square foot. So to build one extra square foot beyond 2000, the cost will be $100. And it may not be a fixed cost, like the cost of building one extra square foot when you already have 2000 might be $100 per square foot. But in the beginning, maybe to build the first 10 square foot, maybe the costs were so much more. So it really depends on where you are in terms of what the cost per square foot is. Doesn't always have to be the same cost per square foot throughout the building process. In the beginning, it might be a lot more. Later on, maybe it reduces because now you've already built, you've already brought the equipment, you've already bought most of the parts, and the labor is already there. Maybe adding one more square foot, maybe it doesn't add that much more to the cost. So let's write that down. Interpret the meaning of f prime of 2000 equals 100. So the cost is of building one additional square foot beyond the 2000 is $100. So we could also say the cost of getting the 2001st square foot, that next one. So when you already have the 2000 built, to build the next one, the cost will be an extra $100. So the rate of cost of building this house is increasing at a rate of $100 per square foot at the moment when there are 2,000 square foot built. Okay. What about part D? Given that f of 2,000 is $275,000, so the cost of building a 2,000 square foot house is $275,000. And use information from part C to estimate f of 2050. What is the cost of building a house that is 2,050 square foot, assuming that cost per square foot will remain constant between 2001 through 2050. So if it's every additional square foot, if that's roughly 100, what will be the cost of building that 2,050 square foot house? So in this situation, we need to find basically f of 2050. So that will be the cost of building the 2,000 square foot house, first of all, 275,000 plus. So you want to build 50 additional square foot at a rate of $100 per square foot roughly. And that will give our answer for the approximate cost of building a house for 2,050 square feet. And that turns out to be roughly, since this is 5,000, added 275, we're going to get $280,000. Again, it's just an estimate because we don't know if the cost per square foot is going to be exactly the same at 2001, at 2002, etc. For linear functions, that's always the same. But for quadratic or nonlinear functions, like sometimes after a point, cost could be decreasing. But here it's always fixed. It's always increasing at a fixed rate. We don't know if our function is linear or not, so we're being super careful in our interpretations. Okay, and for the next question, we have a similar example, but this time we have the W function. The weight of an adult who is consuming C calories is given by W equals G of C, a function. So notice the inside part is C. So the calories go in and the predicted weight will go out. So this is a weight function as a function of calories. We can also write it like this, W of C, the weight as a function of calories consumed. Of course, maybe this, there are many other variables. We're fixing all those other variables. We're only looking at calories versus weight. Maybe we're fixing the height, we're fixing the gender. All kinds of things are being fixed perhaps to do that problem. So trying to do a simplified version of a realistic problem. Okay, so first questions, interpret G of 1800 equals 155. Notice there's no derivative there. It's just, remember, incoming element represents the calories, and this represents the weight in pounds. So when 1800 calories are consumed, we expect that individual to weigh 155 pounds. And calories consumed here, we're going to assume is per day. So interpreting this, when an adult consumes 1800 calories, the weight will be 155 pounds. Again, completely understanding this very simplistic model, but it's just trying to, give another example of the derivatives. So what is the meaning of G prime of C? Again, remember, G of C can also be written as W of C. So now G prime of C can be written as W prime of C. W is the weight. So the rate of change of weight per unit change in calories, I can also write it like this, dW over dC, the rate of change of weight per unit change in calories. That's what it represents. So I'm going to write it down. So G prime of C represents the rate of change of weight per unit change in calories consumed per day. Okay. And given that G prime of 1800 is 0.05 and using information from part A, estimate F of 1850. In other words, W of 1850, meaning the weight of an individual who consumes 1850 calories. So the weight of an individual who consumes 1850 calories. First, we already know the weight of an individual who consumes 1800 calories, right? That is 155. So to find W of 1850, we're going to start with W of 1800, which we already have, plus you go 50 units beyond it, right? So 50 calories beyond it, and for each calorie extra consumed, the rate of change of weight is 0.05. So 50 calories consumed, multiply that by 0.05 to see how many more pounds that individual will be expected to have. So, and we know W of 1800 is 155. So add to that 50 times 0.05. And 50 times 0.05 is 2.5. So now we have 157.5 pounds. So again, we know how to interpret the derivative in context, and we can, if you happen to know the rate of change of something, you know what that quantity is initially, you can make some predictions going a little bit beyond the original values given. Like if you know what happens at 1800, we can use the derivatives to make an estimation what happens at 1850. All right, so those are some applications of derivatives. We talked about velocity, acceleration, and also some examples just in general, interpreting the meaning of derivative in context.